First, thank you for you coming to listen my presentation about my research work. My research goal is to build a knowledge-based question answering system, and I'm from Peking University. My research interest is natural language processing and machine learning. Okay, let's start from a picture. This picture lists most of the knowledge bases that have been widely used in both the academic community and the industrial products. And the colors represent the domains, and a circle's area represents the number of facts in the knowledge base. So you can see we have many domains, and some of them are very big. Actually, as these large-scale knowledge bases have become available, an application called knowledge-based question answering has attracted more and more research interest. The basic task of this KBQA is to answer the natural language question using the knowledge bases. So, for example, given some basic information about the Interstellar, one may ask a question, say, what else did the director of the movie Interstellar direct? Typically, the KBQA system will try to first understand this question, typically by using the semantic parsing-based methods to convert this question into a structured query, and then by executing this query over the database, you can get the answers. Compared to the information retrieval-based methods, this system can get more precise and accurate answers. And my research work actually can be summarized as answering several interesting questions in this task. The first one is what kind of paradigm is appropriate to tackle the KBQA task? You know, many methods have been proposed for this task, and many paradigms have also been used in this to solve this problem. So I will introduce our idea about this question. We will present a more proper paradigm to this task. And the second question, because we know the KBQA system will try to understand this question, so how to represent the meaning of this question and how to recognize this structure. This problem is very interesting, and we will present our structure called a phrase dependency graph to represent the meaning. And the third question is actually more practical, because when we build our real question answering system, we find in many cases the knowledge base can not give you good answers because of the incompleteness of this knowledge base. So here we will present two solutions for this problem to address this. And first, let's see the first question. What kind of paradigm is appropriate to this task? Parallel work can be roughly categorized into two main streams: the semantic parsing-based methods and information extraction-based methods. Typically, most of the semantic parsing-based methods will convert the question directly into a grounded logical form. For example, Barrett proposed a PCFG semantic parser, and Qingjin Cai and Silverreed proposed a PCCG-based semantic parser. Both of these two semantic parsers integrate the semantic parsing into semantic parsing. So when they finish the semantic parsing, they will get the logical forms finally. And in contrast to the semantic parsing-based methods, information extraction-based methods will try to first collect the answer candidates for the question, and then they will propose some ranking methods to rank the answer candidates. For example, Borders proposed a neural network-based ranker, and Xu Yao proposed the lexicalized feature-based ranker. However, we find two limitations for these methods. For the semantic parsing-based methods, we know most of them will try to convert the question directly into a grounded logical form against a specified knowledge base. So we think it will be hard for these semantic parsers to adapt to different knowledge base. So imagine a situation if your task is to answer the question using different knowledge bases, it will be very hard for you to use these semantic parsers. And for the information extraction-based methods, since they don't use many deep understanding technologies, so we think it will be difficult for them to answer the complicated questions. Actually, these are two motivations of our semantic parsers. We hope our semantic parser can have a more generalized ability and can also handle the complicated questions. So before I introduce the details of our semantic parser, let's imagine how we human beings understand the question. For the example question, what else movies did the director of the movie Interstellar direct? Even we human beings don't know the scheme of this knowledge base, for example, FreeBase, DBpedia, Yago, we can still identify some phrases in this question. For example, movies, the director of. We know the director of is a relation, although we don't know which item did this phrase can map to in the knowledge base. So actually, this is the motivation of our semantic parser. We find the meaning recognition is totally independent of the knowledge base, and we can separate the meaning recognition with the meaning grounding. Actually, we will have one more benefit if we do this. We can, first of all, we can focus ourselves on these two subtasks, and then if we can get a meaning, we can ground it into different knowledge bases according to our task. So, and we propose the phrase dependency graph to represent the meaning of our semantic parser. In this graph, the nodes represent phrases and the edges represent semantic relations. We have 4 types of phrases: variable, category, relation, and entity. The variable phrase represents the answer of the question or some intermediate value in the meaning. And the category phrase represents the the knowledge base type. And the relation and the category phrase represent the knowledge base predict and category. Yeah, and you can see this is a graph pattern, and we know the knowledge base keep record of the facts in the triple form: the subject, the relation, and the object. So we can apply simple rules to convert this graph to a structured query.
What's the relationship between the PDG and semantic role labeling?
Sorry.
What is the relationship between your phrase dependency graph representation of meaning and semantic role labeling?
Semantic label.
Semantic role labeling?
Oh, yeah. Actually, I think this task is very similar. But the difference is that the semantic label, we have FrameNet, such semantic roles have been defined. But in our task, we don't have such labels. We also, because we have the knowledge base, so our PDG is actually very similar to the knowledge base. We will have subject, relation, and object.
The PDG is similar to what?
To the structure of the knowledge base.
But I thought you were saying that you were decomposing it from the knowledge base so that the PDG was knowledge base independent.
Yeah, but here we only consider, for example, the relation phrase, we only consider 2 arguments for this relation phrase. We don't have more than 2 arguments.
So relations are binary?
Yeah, binary. Yes.
As distinct from semantic role labeling?
Yeah. And also the category also has 1 argument.
What has 1 argument?
The category phrase.
What's a category phrase?
The category phrase can be potentially mapped to the knowledge base type. For example, the movie, the lake, the river, such as knowledge base type.
The category phrase corresponds to the knowledge base type.
Yeah.
I thought that the PDG was knowledge base independent.
Yeah, actually, I mean the independent is the items we don't know which items did this phrase can map to in the knowledge base, but the structure is very similar. So, yeah, actually, I mean this. Yes.
What's the difference between this and Siva's ungrounded dependency graph?
Actually, we use the different. He uses the logical form to represent the meaning, but I use the graph, and actually the whole process is very similar. He also uses the intermediate language, but in our case we use the structure to represent the meaning.
His tackle paper, like graph matching for semantic parsing,
yeah.
Bruce's representation is almost exactly like this. Isn't that true?
In their semantic parser, their one relation phrase can have multiple arguments, so it will have the graph matching problem in later to map this logical form to the knowledge base structure. But in our case, we only consider 2 arguments. So, yeah. Yes. So next, I will introduce how can we construct this graph for the example question. The first step is to perform the phrase detection and classification. The phrases are categorized into 4 classes: variable, category, entity, and relation. And this task can be viewed as a sequence labeling problem. Here we use the BI scheme to label each token in the question. For example, the VB means the beginning of a variable phrase, and RB means the beginning of a relation phrase. So this is essentially a sequence labeling problem. And we in practice we apply the perceptual model to label the token. The W represents the weights for the features, and F represents the feature vector for instance X along with configuration Y. And we rely on 4 types of features: the post-stack pattern, NER pattern, and the word pattern, and the previous phrase type. Yeah. Then after we perform the phrase detection, we need to find the relationships among these phrases. Here we mainly concern about 3 types of edges. The first one is from a relation phrase to an entity phrase, which indicates that this entity phrase is one argument of this relation phrase. And we also consider the edge from a category phrase to an entity phrase, which here the category phrase categorizes the entity phrase. And the third type is from a relation phrase to another relation phrase, which indicates that these 2 relation phrases will have one shared argument. And this task can also be viewed as a structural prediction problem. And we apply a structural perceptual model to tackle this. And I will give a simple parsing example. If you are familiar with the conventional dependency parsing, this similar is very similar. We use a queue to store the unprocessed phrases and a stack to keep record the processed phrases. And we apply 4 actions: the shift, reduce, arc left, arc right, to construct this graph. And this is our final graph. We can construct this graph only using these 4 actions. So you can see we incrementally construct this graph, and at each step we will have 4 classes: the shift, reduce, arc left, arc right. We have 4 classes. And here features, we mainly concern about the lexical features, the words in these phrases, and the semantic features, the labels of these phrases, and the structural features, the in degree or out degree of these phrases. Experimental results showed that the structural features are the most important in this subtask.
Can I ask a question? What are the semantics of the links that you're inferring?
Semantic features are the semantic label assigned in the first step. For example, the variable phrase, category phrase, relation phrase.
Yeah, but then the connections between them. So if you connect a relation to a relation,
Yeah.
what does the connection mean?
These 2 relations will have one shared argument. For example, yeah, one argument of relation A is also the argument of relation B.
And what about between an entity and a relationship?
The entity phrase is one argument of this relation phrase. Yes.
Do you know which argument?
No, we don't care about a subject or object. We will do this in the next step. Yeah. We evaluate our system, this semantic parser on 2 datasets, Free 917 and Web Questions. The Free 917 involves 900 questions with annotated logical forms. We convert these logical forms into phrase dependency graph we use in our work. And for the Web Questions, we have 5,000 question answer pairs. I will mention one thing about these 2 datasets. These 2 datasets are both of them are for the free base, but the Web Questions will involve more domains than Free 917. And we train our semantic parser just on the Free 917 and directly test our semantic parser on Web Questions. So this is our result. We use the phrase dependency graph accuracy to evaluate our semantic parser, and on Free 917 we will obtain 69% accuracy. And on Web Questions, we can get a higher performance. This is very interesting because we don't touch the training data in Web Questions. We just test our semantic parser. So I think the reason is that the questions in Free 917 are more difficult than those in Web Questions. And during the training, our semantic parser has has seen many complicated questions, so we can understand these questions in web questions. So this is very simple.
What is this accuracy? Like, what does that number mean?
If the predicted phrase dependency graph, the ages and the phrases are totally correct, we will consider this PDG correct. If one phrase or age is not correct, we will think this PDG is incorrect.
And then you also annotated these graphs for web questions to do the evaluation?
Yeah, we also actually manually annotated the PDG for web questions. Yeah. Actually, this result also indicates that if our semantic parser, during the training, we can feed some complicated questions to our semantic parser. We can correctly understand this question. Yeah.
So you annotated all of the 5,800 web questions with these PDGs?
Yeah.
So why didn't you train and test on, like, how does it do if you train on that instead of training on 319? I guess you'd have to do cross-validation, but.
Yeah, I know. During the other work, we didn't try this. We just, this may be a good question. We can try this on web questions, but at that time we only train our semantic parser on 3917. Yeah.
And do you have like a baseline, for instance, like Siva and other people, like Kwiatkowski, that have these like intermediate logical forms or similar, like where you basically do a deterministic transformation of some kind of tree, and then you get this. And so, do you have some kind of baseline to compare against?
No, I don't think so. At that time, we only, at that time the Siva's paper hadn't been published, so we only evaluated using this PDG.
Let me ask one more question. Don't these data sets have some quantifiers? Like 3917 has a couple quantifiers for sure. I think web questions has a few too, right? Like counting. Yeah. So you can't represent that in your phrase dependency graph.
Yeah, so I will introduce later. We will use many rules, some rules to, for example, how many we will convert this. When formulating the structure query, we will convert the how many to aggregation operation, count x. Yeah.
But you just can't do it here.
Yeah, we can do it here. Yeah.
As I understand, there's two parts to the parsing. The first part is labeling the words and phrases into the categories you've defined.
Yeah.
And then the second part is doing the mapping. The links.
The relationships
So
among
did
this.
you do an error analysis on the two parts separately? Like, where are the errors coming from? Are they coming from the classification part or from the linking part?
You mean the error?
Yeah, the error rate here seems to, I can't tell from this where the errors are coming from. Are they coming from the first stage
Okay.
where you do the categorization, or the second stage where you do the links?
We actually, in the paper, we evaluated these errors. We will count how many errors are from the phrase detection and some of, on what percent are from the phrase dependency parsing, but I didn't list the result here.
Do you remember which one is?
Actually, the second part, the phrase dependency parsing is more errors are from the phrase dependency parsing. Yeah, because the manner we human being ask a question actually are very similar. So in the first step, we can get, I remember, 90% accuracy on the phrase detection result. We can get the correct phrase detection result, but in the second step, we will get a lower performance. Yeah.
Do you know why the web questions have quite a bit higher accuracy? What is it about them that makes them easier?
Because according to the account by Yao Xuchen, 80% of the web questions are simple questions, which I mean involves only single entity or single relation. So for these questions, our semantic parser can do very well for these questions. Yeah, because the 3917, the questions in 3917 are more complicated. Typically will involve at least two entities and at least two relations. Yes.
One last question. Do you do any kind of normalization of the text that you see, or are the relations and stuff that you predict always strict substrings of the sentences themselves? Does that make sense?
Sorry, I don't know.
So if you go back a few slides, so here, the director of is a phrase that appears directly in this. Like when you talk about semantic parsing, typically it's mapping from these symbols into some kind of structured representation. Where typically you do some kind of normalization of this text, but you're using the string directly here as your relation phrase. Is that right?
Yeah, right.
Okay.
Yeah, I will show you later.
Okay.
And before I talk about the other part, I will talk about this. One common problem. We will have the error propagation problem because we are in a pipeline literature. The errors will propagate from the phrase detection to phrase dependent parsing. So to address this, we propose the joint inference approach. This part is very complicated. So if you are interested, we can talk about this later. I will talk about this basic idea of this joint inference approach. If we are in a pipeline literature, we will consider the top-ranked result in local components. To address this, we will consider more than one result in each component, maybe 5 or 10 results in the local components. And then we hope in some cases we can construct the correct PDG from the results of these two components. And the features over here we consider actually are the combinations of these two components. Yes. And then after we have got the PDG, the last step is to ground it to a structured query. Here we consider two knowledge bases. Because we separated these two parts, so we can ground the meaning against two different knowledge bases. And one intuitive solution is to find a global optimal grounding result during the grounding. But I think it will involve too large search space to solve. Actually, for even one phrase, the knowledge base can give you many candidates for it. So I think it will involve too large search space to solve. So we propose the second solution to find a local optimal grounding result. We also use a perceptual model to tackle this from the left to the right. And then we will use some global features to help us to determine which item do these phrases can map to. And here features we concern about the lexical features, local candidate scores returned by the tools, the entity linking tools, the relation extraction tools, and we also rely on some knowledge base related features here. And these are the rules for us to convert the PDG, the grounded PDG, to a structured query. We only rely on these 10 rules to solve these questions in web questions and free 917. Actually, you can see after we doing this, we can construct a simple or naive QA system. And when we build our real systems, we find the most challenging problem here is to perform the relation extraction. Because we have too many challenges. First of all, there are thousands of predicts in the knowledge base, so this problem itself is very challenging. And since we have so many predicts, so we have to automatically construct the training data for our relation extraction part. And so these data are noisy, so how to learn a robust relation representation from such data is very interesting. And so we focus ourselves in this subtask, and we hope we can build a novel relation extractor for the QA task, for the QA system. And the basic task definition for the relation extraction is to predict the relationship between these two phrases in a sentence. These are the basic definition of this task. And prior work have used many features such as post-tag feature, word-net feature, frame-net, and dependency path features. Among these features, the semantic features are considered the most useful in this task. We have tried many semantic features and find the shortest dependency path is the most useful in the semantic features. For example, the recipient receives the call through a miniature radio receiver carried on his person. The receiver and the recipient will have a relation called the instrument agency here. And the shortest dependent path will go through, carry the radio through receives. We think this predict sequence can represent the meaning of this relation. And we want to learn the relation representation from this path. Why we do this? Because we imagine we have two situations. If these two mentions are in the same predict argument structure, then the shortest dependence path will definitely go through this predict, this main predict. If these two mentions are in different predict argument structures, the shortest dependence path will go through a sequence of predicts, actually can also represent the meaning. So this is the reason why we try to learn the relation representation from the shortest dependence path. And this is our model. We apply a multi-channel convolutional neural network to learn this representation from both the dependence path and the coarse context. We will have two channels. The first channel will take the path between these two mentions as input, and the second channel will take the coarse context around to these two mentions as input. The reason why we consider two channels is that in some cases, the shortest dependence path is too short to give you enough information to predict the relation. So here we consider two channels. And each channel will follow the standard convolutional neural network model. And we will combine these two feature vectors together and use this vector to predict the knowledge-based relation. Yes. And this is our loss function for training. We use the cross-entropy error to train our neural network. And we use static gradient descent to update the parameters. Here I also want to introduce a technology called negative sampling. This technology is different from that used in training the word vector. In the conventional relation extraction, one don't know which mention is the subject of or object of this relation. So they will convert the k relation task into 2 times k relation task, right? Because they don't know which mention is the subject. But we find the shortest dependent path is actually directive, and if during the training we can treat the shortest dependent path from the subject to the object as positive example, and the reversed path as negative example, you can get a higher performance. So this technology can help us to distinguish which mention is the subject or object of this relation. And we evaluate our relation structure on 2 datasets, the semi-evaluated task 8 and the web questions. Because the reason why we evaluate our system on semi-evaluated is we hope to see if our relation structure can also perform very well on this conventional relation extraction task. And this task involves 10 relations and 8,000 sentences for training and 2,000 sentences for test. And the web questions will involve 461 relations, and we use 3,000 questions for training and 2,000 questions for test.
Question: where did those 461 relations come from for web questions?
From Freebase.
So annotated logical forms? Web questions just has text and answer.
Yeah, we will actually we will enumerate all possible relations during the pre-process, and we will check which relation is most probable to this question by computing the F1 value of the answers.
So there are 461 relations in the Freebase version that was used for web questions.
Yeah.
And then you're doing some heuristic annotation of the training questions using that set.
Yeah.
Okay.
So you said you use the dependency features for this. What's the relation with the PDGs?
Because we hope to build a relation structure here and then apply this relation structure in our grounding the PDG.
Okay. So you have relations in the PDG.
Yeah, we will have a relation structure in PDG. In PDG we have relation phrase, so you need to ground this relation phrase to knowledge-based predict.
Oh, I see. Okay, so if there's a relation phrase in the PDG.
Yeah. We will use this
This is
to.
what you're using to ground it.
Yeah, right. Yeah.
Are there any reflexive, like married to relations in semi-val or web questions, where both directions?
Yeah, right. You mean the media node for some events?
Like for your negative sampling, you consider if subject-object is positive, you consider object-subject to be a negative example.
Yeah.
That's true in most cases, but in things like married to these reflexive relations where x, y, and y, x both are true, do you do something special or does that?
Actually, this negative sampling method is proposed for the conventional relation extraction task. You know, if we use the web questions using the free base, we know the type of the subject and the type of the object. So we can identify which one is the subject of this relation. Yeah. In many cases. Yeah. So this technology is for the conventional relation extraction task.
I think you mean symmetric, by the way, not reflexive.
Oh yeah, sorry. That's
And the answer is none of them are symmetrical.
okay.
Is that the answer?
Sorry?
Are any of the relations you're dealing with symmetric?
Symmetric.
Symmetric relation means that r of xy is equal to r of yx.
No. Actually, in the conventional relation extraction task, the relation are the ones you mentioned.
Are not symmetric.
Actually, I think symmetrical in many cases. Yeah.
I was sort of involved in semi-val 2010, and my memory is that none of the 10 relations are symmetrical.
Yeah. And these are our results on the semi-evaluated task 8 dataset. If you can see these two results, you can see the depth LCN will consider the dependency label when modeling the relation representation. So you can see if the dependency label can also boost the relation extraction performance. And if you compare these two results, you can see the negative sampling will give a huge performance improvement on this data set, about 2 points. Yes. And we also apply this relation extractor in our PDG semantic parsing framework. We evaluate our relation extractor using the relation extraction accuracy. We also use a baseline naive-based model. The naive-based model uses many data from the clue app to learn the occurrence among the predict and the words. And it achieves 30% on the relation extraction accuracy. But our model will achieve more higher performance, 45% on this dataset on the web questions. And you can also see the QA performance can also be improved if you apply the DLCN here. Yeah. Actually, when we analyze the errors of our system, we find 80% of the questions are simple, which involve only single knowledge-based relation, and the left questions are complicated, which involve at least 2 knowledge-based relations. So we wonder if we can use some more simpler methods to solve the KBQA task. And this is the motivation of our relation extraction-based QA framework. Imagine that actually, in many cases, people ask a question, they mention some entities in the question. They just want to mention the relationships among these entities and the answers. So we convert the QA task into a relation extraction task. And the goal here is to predict the relations among the answer and the entities in the question. And here is the free-base graph. So this task actually is equals to finding the relation paths between the answers and the entities. Once we can find these paths, we can get the answers. So this is a very simple framework, and we only have an entity linking part and a relation extraction part. And here we will perform a joint inference to find the global optimal assignments for the entities and the relations. And the reason why we do the joint inference is that if we use the pipeline literature, the error also will propagate from the upstream entity linking to the downstream relation instruction. So we propose this joint inference approach. And the training data is created as follows. If the predicted entity and equals the gold entity and the predicted relation equals gold relation, we will assign this triple a score of 3. If only the entity are correct or the relations are correct, we will assign a score of 2. Otherwise, we will assign a score of 1. We use this to train a SVM ranker to this task. And here we've used 3 types of features: the entity clues, relation clues, and answer clues. The answer clues are non-local because we query the database using the entity and the relation. Actually, when we build this system, we find some questions that our system cannot answer. These questions are very interesting. For example, what mountain is the highest in North America? Because this question involves aggregation operation highest, so one has to rank the candidate mountains according to their heights. The second question is who did Shaq first play for? The reason is the same. You have to create a rule to rank the teams according to the date. So how to deal with this question? Fortunately, we find the text resources such as Wikipedia can give us such information to refine the answers. For example, for the third question, who is Shaq's father? We can find a sentence in Shaq O'Neal's Wikipedia page. O'Neal was drafted by the Orlando Magic with the first overall pick in the NBA draft. If we can understand this question, we know, the draft team is the first team, so we can answer the second question. So, this is the motivation of our framework. The first step is to perform the KBQA system. We will use this system to get some candidate answer for the question, and then we will use the Wikipedia to refine these answers. And this is our model. For each candidate answer, we will search the sentences in the Wikipedia page to support this answer, and we will develop a refinement model to make a judgment for this candidate answer. And if correct, we will treat this answer as final answer. Yeah. And this is our refinement model. The first step is to locate the topic entity in the Wikipedia dump, and the second step is to extract the content and treat the sentences that contain the candidate answer as evidences. And then we will develop a SVM classifier to perform the prediction. Here, the features are the word pair features. The first gram is from the question, and the second gram is from the sentence. Yeah. And these are some results. What is the largest nation in Europe? You can see if we don't take the textual-based inference, we can have multiple answers. But if we can perform this inference, we can get the final answer, Russia. So in some cases, this technology can help us better refine the answer retrieved from the knowledge base. And these are the results on the web questions. We can see if we apply the structure inference, the KBQA system, and the joint inference for the relation instruction and entity linking and unstructured inference over Wikipedia, we can get the highest performance on this data set, a slightly better than in Microsoft. But I should mention that Yin use many rules to address the question, to deal with the questions I just mentioned. So this result indicates that Wikipedia can help KBQA better understand the questions.
So the link between first played for and drafted by is very domain specific, very it's not easy to guess, like unless you know the language of NBA.
Yeah.
How much variety of such things you had in these questions, and how much training data did you need to figure that out?
The training data actually is totally from the web questions. Yeah, for these training questions in web questions, we will first perform the knowledge-based question answering system, use this technology to get the answer candidates. And then we will construct the training data according to these answer candidates to train our Wikipedia-based inference. You mean entity linking?
Entity.
Entity linking, we apply the smart entity linking tool in the web questions. We don't develop such tools. And yes, if we compare the result of struct and struct plus joint, we can see the joint inference can also improve the relation instruction and entity linking performance. Actually, this system also has a limitation. You see, the overall system performance is bounded by the knowledge-based question answering part. So if we don't have answer candidates in the first part, we cannot get the final answer. For example, in the question, who is the frontman of the band that wrote Coffee and TV? For this question, the frontman cannot be understood by knowledge base, so we cannot get the answer candidates in the first part. So we need to find a better solution to deal with such question. And this is our hybrid QA framework. In this work, we will consider both the free text and knowledge base together to understand such question. The first step is to perform the question decomposition. We will decompose this question into several parts. Each part will have 3 parts: the subject, relation, phrase, and object. Yeah, and then we will use a triple solver to solve each triple in the first step to find the answer candidates. The triple solver will involve entity linking and knowledge-based relation instruction part and the textual relation instruction part. So for this example is the frontman of, we can use the OpenIE relations to understand this part. And once we do this, we can understand this question. And then we will perform a joint inference over these assignments to find the optimal assignments for these entities and relations.
So you've got a paraphrase model here.
Yeah, right.
So maybe I missed that. So how are you learning the paraphrases?
I will introduce here. I will introduce later. The paraphrase model here, we use the autoencoder and autodecoder models proposed by Social to do the paraphrasing. And we will have an external external data set to train the paraphrasing model.
What was the external data set?
That data set is also used in Social's paper. I just don't remember the name. Yeah.
Sorry, one more detail. When you use the Open Information Extractor over the Wikipedia dump, what Open Information Extraction system did you use?
Stanford Open Relation Instructor.
And how well did it work?
I think very good for such questions. We can get a good performance on Wikipedia dump.
How can you tell? Just by inspection, or?
Because we check our questions, and we find in many cases the results of Open Information Extractor can give us some text relations that can correspond to this relation phrase. So I think this is enough for our task, at least on the dataset QLD. And the entity linking, because we evaluate our system on 2 datasets, the QLD dataset and the web questions. The QLD is for DBpedia, so we apply 2 entity linking tools: the smart entity linking tool and the DBpedia lookup tool to do the entity linking thing. And for the knowledge-based relation extraction, we apply our neural network-based model to predict the relation. And for DBpedia, we use the party dataset to train our relation structure. Yeah, this is the third part, the text relation instruction. We first perform the open relation instruction on the Wikipedia dump, and we will get a textual knowledge base, and then we train our paraphrase model to map the relation phrase to the OpenIE relation. Yeah. And this is our joint inference. We will need a joint IOP model to perform this joint inference. Here, I should mention that in many cases, we allow the joint inference to choose both the knowledge-based predict and the textual relation for the same relation phrase. Actually, if these two predicts, if these two relations are coherent, that is what we want to see, because this can give us more higher confidence for these assignments. But if these two relations are not coherent, we will choose the one with higher score. So this is our objective function. The first part is entity linking and relation extraction. This part will involve two parts, two subparts: the knowledge-based relation extraction and the textual relation extraction. And the third part is actually designed to evaluate the coherence between the entities, knowledge-based relations, and the textual relations, and the sum of these scores. And these are our constraints. The first constraint is designed to guarantee one entity mention can be mapped to at most one knowledge-based entity. And these two constraints are designed to guarantee one relation phrase can be mapped to at most knowledge-based predict or textual relation. And we evaluate our system on these two datasets, the QLD6 and the web questions. The QLD6 is released this year. Each question in this dataset cannot be answered only using the Freebase or DPP, such knowledge bases. But for the web questions, these datasets are designed to evaluate the knowledge-based question answering system. And we evaluate our system on web questions because we want to see if the textual resources can also help us improve the performance for the KBQA system. And these are our results. We can see on the web questions, we cannot get much higher performance improvement here. But on the QLD, this dataset, we can get almost 30% F1 values on the answers. Yeah, this is this work is just published in this Colin this year. And we built our real question answering system, Chasa, and it has won the first prizes in the recent QA tracks. And so these are our conclusions. We first proposed a pipeline framework to tackle KBQA tasks and introduce the PDG to represent the meaning. Here I want to talk more about the PDG. Actually, I think the PDG is very flexible because in many cases we have the aggregation phrases. We can additionally add this type of phrases in our PDG, and we can also construct the graph according to your task. So I think this structure is very flexible. And when grounding the meaning representation, we propose a multi-channel convolutional neural network to learn the relation representation. And on the RE dataset, our system also obtains the state-of-the-art performance. And the third is we propose a refinement model to help a KBQA system better understand the questions. And we also introduce a hybrid QA framework which exploits both the knowledge base and the free text to answer questions. Yeah. And these are the publications for this work. Thank you.